Uranus, the second farthest planet from the Sun, and the one planet that turns every grown adult back into a giggling child. It is fine. We have all been there. But what this planet is actually doing is no joke. Every world in our solar system follows the same basic rules. They spin upright. Their magnetic fields align with their rotation. They radiate heat left over from their formation. Uranus breaks all of them. This planet is tilted 98 degrees on its side, rotating like a barrel rolling through space. Its magnetic field points in the wrong direction, offset from its center by a third of the planet's radius. It emits almost no internal heat, despite being 14 times more massive than Earth. Every rule we built to explain how planets behave, Uranus violates. Scientists have spent decades trying to explain why. The answer is rewriting how we understand planet formation across the entire galaxy. If you enjoy journeys into the strangest corners of our solar system, do me a favor and hit that like button and subscribe. Now, get yourself comfortable. Let's begin. Before you can understand what Uranus did wrong, you have to understand what every planet is supposed to do right. There is a rule book, not a literal document sitting in a filing cabinet at NASA, but a set of physical expectations so deeply embedded in the mathematics of planetary formation that scientists treat them as inevitable consequences of how solar systems assemble themselves. Every planet we have studied in detail, every moon, every exoplanet whose properties we can measure, confirms these expectations to varying degrees of precision. The rules are not guidelines. They are predictions that emerge directly from the laws of physics applied to a collapsing cloud of gas and dust. And for 7 out of 8 planets in our solar system, they work beautifully. The story starts 4.5 billion years ago with a cloud of molecular hydrogen, helium, and trace amounts of heavier elements drifting through the interstellar medium of the Milky Way. Something disturbed this cloud, perhaps a shock wave from a nearby supernova, perhaps a gravitational nudge from a passing star. The cause matters less than the consequence. A region of the cloud became slightly denser than its surroundings, and gravity did the rest. Once a clump of gas is dense enough, its own gravitational pull begins drawing in surrounding material, and the process accelerates. More mass means more gravity. More gravity means more mass pulled inward. The cloud began to collapse. This is where the first rule was written. The collapsing cloud was not perfectly still. Like virtually everything in the galaxy, it had a slight rotation, an inherited angular momentum from the larger molecular cloud complex it belonged to. As the cloud contracted, conservation of angular momentum forced it to spin faster. This is the same principle that makes a figure skater accelerate when they pull their arms tight against their body. The total angular momentum cannot change, so as the radius shrinks, the rotational speed must increase. The collapsing cloud spun faster and faster as it contracted, and that spin had a structural consequence. Material falling inward could not easily fall toward the rotational poles because the centrifugal effect pushed it outward perpendicular to the spin axis. Instead, material accumulated in the plane of rotation, spreading outward like pizza dough, flattening as it spins. Within a few 100,000 years, the collapsing cloud had transformed into a structure that would define the geometry of everything to come. A hot, dense protostar at the center, surrounded by a vast rotating disk of gas and dust extending billions of miles outward. This was the protoplanetary disk, the birthplace of every planet, moon, asteroid, and comet in our solar system. The disk was not a peaceful nursery. It was a violent, chaotic environment where temperatures near the young sun exceeded 2,000 degrees and pressures varied by orders of magnitude across its extent. Close to the protostar, only the most refractory materials could survive as solids, metals, and silicate minerals that could withstand the searing heat. Farther out, beyond a boundary called the snowline located roughly where the asteroid belt sits today, temperatures dropped below the freezing point of water. Ice grains could survive there, and beyond the snowline, ammonia ice and methane ice condensed at even greater distances. This temperature gradient across the disk determined what materials were available for planet building at each distance from the Sun, a detail that would become critical for understanding the difference between gas giants and ice giants. Within this disk, the process of planet formation began with the smallest possible steps. Microscopic dust grains, each no larger than a particle of cigarette smoke, collided gently and stuck together through electrostatic forces. These fluffy aggregates grew into millimeter-sized pebbles, then centimeter-sized clumps, then meter-sized boulders. At this point, the growth process hit a notorious obstacle called the meter-size barrier. Objects of this scale are too large for electrostatic forces to hold together upon collision, but too small for gravity to bind them. Many collisions at this stage result in destruction rather than growth, shattering boulders back into rubble. How the solar system overcame this barrier remains debated, but the leading theory involves a process called streaming instability, where drag forces between gas and solid particles concentrate pebbles into dense clumps that collapse directly into kilometer-sized planetesimals under their own. Gravity, bypassing the problematic intermediate sizes entirely. However it happened, the disk eventually produced trillions of planetesimals, rocky and icy bodies ranging from kilometers to hundreds of kilometers across, each one a building block for the planets to come. What followed was a demolition derby in slow motion. Planetesimals collided constantly, sometimes gently enough to merge and grow, sometimes violently enough to shatter each other into fragments. The largest bodies had a gravitational advantage. Their stronger pull attracted more material, making them grow faster than their smaller neighbours. This runaway growth produced a handful of planetary embryos, objects roughly the size of Mars or larger, that dominated their orbital zones and swept up remaining planetesimals over millions of years. The final stage of planet formation involved collisions between these embryos themselves, each impact a cataclysm that could melt entire worlds and reshape their compositions. This violent assembly process is important to keep in mind, because it means the early solar system was nothing like the orderly arrangement of planets we see today. For the first several 100 million years, the outer solar system was crowded with debris, crisscrossed by objects on unstable orbits, and punctuated by collisions that could alter a planet's trajectory, composition, and spin in a single event. The rules we are about to discuss describe what should emerge from this chaos once the dust settles, but the chaos itself left marks on every world that survived it. Some marks are subtle, others, as we will see, are not. The disk established the first and most fundamental rule of planetary formation. Everything orbits in the same direction. The disk rotated as a coherent structure, and every particle of dust, every grain of ice, every molecule of gas within it shared that rotational direction. When these particles began sticking together through electrostatic forces and gentle collisions, the resulting clumps inherited the disk's rotation. When those clumps grew into kilometer-sized planetesimals through continued accumulation, they carried the same angular momentum. When the planetesimals collided and merged into protoplanets, the combined bodies preserved the overall rotational trend. The entire process, from microscopic dust grains to giant worlds, was threaded through with a single shared rotational direction inherited from the original cloud. This inheritance produces a specific, testable prediction. Planets that form from a protoplanetary disk should spin in roughly the same direction as their orbital motion around the central star, and their rotation axes should be approximately perpendicular to the plane of the disk. Small deviations are expected. The final stages of planet formation involve collisions between protoplanetary bodies, and these impacts can nudge a planet's spin axis a few degrees in one direction or another. But the baseline expectation is clear. A planet born from an orderly disk should spin mostly upright, with its axis within maybe 10 or 20 degrees of perpendicular to its orbital plane. Jupiter confirms this prediction with almost mechanical precision. The largest planet in our solar system has an axial tilt of just 3.1 degrees. It spins nearly perfectly upright, completing a full rotation in just under 10 hours despite being over 11 times the diameter of Earth. This rapid spin is itself a relic of formation. As material from the disk fell onto the growing protoplanet, it carried angular momentum with it, spinning Jupiter faster with every accretion event. The planet's tiny tilt tells us that nothing catastrophic disrupted its orientation after it assembled. It grew, it accumulated its massive hydrogen and helium atmosphere, and it settled into a stable configuration that has persisted for the entire age of the solar system. Jupiter is the textbook example of a planet that followed every rule the disk imposed. Saturn provides a slightly more nuanced conformation. Its axial tilt of 26.7 degrees is larger than Jupiter's, but still comfortably within the range that formation models accommodate. Recent research suggests that Saturn's tilt may have increased gradually over billions of years through a gravitational resonance with Neptune. As Neptune's orbit slowly evolved, it created a periodic gravitational tug on Saturn's spin axis that pumped energy into Saturn's obliquity over cosmic timescales. This process, called spin-orbit resonance, is well understood mathematically and does not require any unusual events. Saturn started with a modest tilt and gained a few extra degrees through a slow, predictable interaction with a neighbouring planet. The explanation is clean, the physics is settled. Saturn cooperated. Even Venus and Mercury, which have their own rotational oddities, do not fundamentally challenge the framework. Venus rotates backward compared to most planets, with a retrograde spin that may have resulted from atmospheric tidal interactions with the Sun or a combination of gravitational effects over billions of years. Mercury's rotation is locked into a 3-to-2 resonance with its orbit due to solar tidal forces. These are modifications to the baseline prediction, not violations of it. The underlying physics still applies. The outcomes are explainable through known mechanisms operating over known timescales. The second rule concerns magnetic fields, and understanding it requires diving beneath a planet's visible surface into the extreme conditions of its deep interior. Giant planets generate magnetic fields through a process called a dynamo, which works on the same basic principle as a hydroelectric generator. Electrically conducting fluid moves through an existing magnetic field, which induces electrical currents in the fluid, which in turn generate their own magnetic field, which sustains the whole cycle. The key requirements are a fluid that conducts electricity and enough energy to keep that fluid moving through convection. Inside Jupiter, conditions are so extreme that they create an exotic state of matter found nowhere on Earth's surface. At depths of roughly 20,000 kilometers below the cloud tops, the pressure of the overlying atmosphere reaches millions of times Earth's sea level pressure. Under these crushing conditions, hydrogen molecules are squeezed so tightly together that their electrons detach and flow freely between atoms. The hydrogen stops behaving like a gas and starts behaving like a liquid metal. This metallic hydrogen conducts electricity brilliantly. Convection currents driven by the planet's internal heat stir this conducting fluid in complex patterns, and the resulting dynamo generates a magnetic field so powerful it extends millions of kilometers into space. The critical prediction is about geometry. Because the planet's rotation organizes the convection currents that drive the dynamo, the resulting magnetic field should align approximately with the rotation axis. The spin determines the flow patterns. The flow patterns determine the field. Therefore, the field should point roughly in the same direction as the spin. Think of it as placing a bar magnet inside a spinning globe. The magnet naturally aligns along the axis of rotation because that is the direction the internal flows are organized around. Jupiter confirms this beautifully. Its magnetic field is tilted only about 10 degrees from the rotation axis. Saturn is even more precise, with a magnetic tilt of less than 1 degree. These measurements validate the dynamo theory and establish the expectation that well-behaved giant planets should produce magnetic fields closely aligned with their spin axes. Small offsets are acceptable. They arise because the conducting fluid inside the planet is not perfectly uniform, and the convection patterns have some asymmetry. But the fundamental alignment should hold. Rotation drives the dynamo. The dynamo produces a field along the rotation axis. The magnetic poles should be near the geographic poles. Earth follows this pattern as well, with a magnetic field tilted about 11 degrees from the rotation axis, generated by convection of liquid iron in the outer core. Even Mercury, the smallest planet with an active dynamo, produces a dipole field roughly aligned with its spin. Across every planet where we have measured a magnetic field, the same pattern repeats. The field follows the spin. The dynamo obeys the rotation. The third rule is thermal, and it connects directly to how planets form. Giant planets are expected to radiate more energy than they receive from the Sun, not because they generate power through nuclear fusion like stars, but because they are still cooling down from the tremendous gravitational energy released during their assembly. When a giant planet forms through the accumulation of gas and solid material over millions of years, the gravitational potential energy of all that infalling matter converts to heat. The deeper the material falls into the planet's gravity well, the more energy it releases. By the time a planet like Jupiter finishes forming, its interior is scorching, tens of thousands of degrees at the core, far hotter than the surface of the Sun. This primordial heat does not dissipate quickly. The planet's own mass acts as insulation. Heat from the deep interior must work its way outward through thousands of kilometers of increasingly less dense material before it can radiate into space from the cloud tops. This process takes billions of years. The planet acts like a massive thermal reservoir, slowly leaking the energy it accumulated during formation. Measurements confirm this prediction across multiple planets. Jupiter radiates approximately 2 times more energy than it absorbs from the Sun. That excess comes entirely from the slow release of internal heat accumulated during formation. After 4.5 billion years, the largest planet in the solar system is still measurably warm from its own birth. Saturn tells an even more dramatic version of the same story, emitting more than twice the energy it receives from the Sun. Part of Saturn's excess may come from an additional process, the gravitational separation of helium from hydrogen deep in the interior, which releases extra energy as the denser helium sinks toward the core. But the fundamental mechanism is the same. The planet formed hot and has been cooling ever since. Think of it like a pressure cooker with the valve sealed shut. You pour energy in during formation, the planet's gravity traps that energy inside, and it takes billions of years to slowly bleed out through the thick layers above. Every giant planet should have this thermal afterglow. The bigger the planet, the more energy it's stored. The thicker the insulating layers, the longer it takes to cool. 4.5 billion years is simply not enough time for a planet the size of Jupiter or Saturn to have fully released its formation heat. These 3 rules, upright spin, aligned magnetic field, and ongoing heat emission, form the backbone of our understanding of how giant planets work. They are not arbitrary expectations or hopeful guesses. They are direct, calculable consequences of the physics governing gravitational collapse, angular momentum conservation, magnetohydrodynamics, and thermodynamics. Any planet that forms from a protoplanetary disk through standard accretion processes should exhibit all 3 properties. And for the gas giants Jupiter and Saturn, the agreement between prediction and observation is remarkably tight. Now comes the classification that matters most for this story. Jupiter and Saturn are gas giants. They are composed primarily of hydrogen and helium, the 2 lightest and most abundant elements in the universe, with relatively small, rocky and icy cores buried deep beneath their enormous atmospheres. Their bulk composition closely mirrors the original protoplanetary disk, because they formed early enough and were massive enough to capture vast quantities of the disk's dominant gases before they dissipated. Uranus and Neptune belong to a different category entirely. They are ice giants. The name is misleading if you picture frozen ponds and glaciers. In planetary science, the word ice refers not to temperature, but to chemical composition. It describes a group of volatile compounds, primarily water, ammonia, and methane, that condensed as solid grains in the outer regions of the protoplanetary disk where temperatures dropped below their freezing points. These icy grains accumulated into the cores of the outer planets, but Uranus and Neptune never grew massive enough to capture the enormous hydrogen and helium envelopes that characterize Jupiter and Saturn. The reasons for this are still debated, but both leading explanations trace back to the challenges of building a planet in the outer solar system. One explanation is timing. Uranus and Neptune may have formed later than the gas giants, assembling their cores after the protoplanetary disk had already begun losing its gas. The young sun's increasingly intense radiation and powerful stellar winds gradually stripped gas from the disk over its first few million years. Jupiter and Saturn formed quickly enough to grab massive gaseous envelopes before this gas was lost. Uranus and Neptune were slower. By the time their cores reached the critical mass needed to begin capturing large amounts of hydrogen and helium, there simply was not enough gas remaining in their orbital neighborhood to capture. The second explanation involves distance. Forming farther from the Sun meant slower orbital speeds, longer orbital periods, and therefore fewer collisions between planetesimals per unit time. The feeding zone of each growing protoplanet was larger in the outer solar system, but the material within it was more spread out. Accretion was a slower, more painstaking process out there. Planetesimals took longer to find each other, longer to collide, longer to merge. The ice giants ran out of time before they ran out of potential building material. Whatever the cause, the result is a planet with a fundamentally different internal structure from a gas giant. The interior of an ice giant is thought to consist of a small rocky core, perhaps a few Earth masses, surrounded by a vast mantle of water, ammonia, and methane compressed to extreme densities. These compounds do not exist as recognizable ices at the pressures and temperatures found inside Uranus. They form hot, dense fluids that behave in ways laboratory chemistry is only beginning to explore. Above this icy mantle sits a relatively thin envelope of hydrogen and helium mixed with methane, which transitions into the visible atmosphere at the top. The methane absorbs red wavelengths of sunlight and reflects blue, giving both Uranus and Neptune their distinctive colors. The structural difference between gas giants and ice giants is not just a matter of degree, it is a difference in kind. Jupiter is roughly 90% hydrogen and helium by mass. Uranus is roughly 80% water, ammonia, and methane by mass. They are made of fundamentally different stuff, arranged in fundamentally different ways, with fundamentally different physical processes governing their interiors. This distinction matters because it determines everything from how the planet generates its magnetic field to how efficiently it transports heat from its core to its surface. Models built for gas giants do not automatically apply to ice giants. The physics is different because the materials are different. The crucial expectation, then, is this. Uranus and Neptune should behave like siblings. They have nearly identical masses. Uranus weighs in at 14.5 Earth masses, Neptune at 17.1. Their diameters differ by less than 4%. Their bulk compositions are believed to be broadly comparable. They formed in the same general region of the outer solar system, from the same reservoir of icy and gaseous material, subject to the same physical processes. If the rules of planetary formation apply consistently, these two worlds should be approximate twins, not identical, but close. Similar tilts, similar magnetic fields, similar thermal properties, similar atmospheric dynamics. Two variations on a single theme. Neptune, to its credit, largely cooperates. Its axial tilt of 28.3 degrees falls comfortably within the normal range for solar system planets. Its atmosphere is violently active, with the fastest sustained winds measured anywhere in the solar system exceeding 1,200 miles per hour. Dark storm systems appear, evolve, and dissipate across its vivid blue disk. Bright companion clouds of methane ice crystals form at high altitudes, casting shadows on the deeper cloud layers below. The planet looks alive, dynamic, energetically driven by processes that planetary scientists can identify and model with reasonable confidence. Its magnetic field is unusual, tilted about 47 degrees from the rotation axis, more than any gas giant. But the dynamo is recognizably active, and the field configuration can be explained by models of how conducting fluids behave in ice giant interiors. Scientists noted the tilt as interesting, perhaps hinting at the different interior structure of ice giants compared to gas giants, but not alarming. It was a variation on the theme, not a contradiction of it. Most importantly, Neptune radiates significant excess heat. It emits approximately 2.6 times more energy than it absorbs from the Sun, despite orbiting even farther from the Sun than Uranus, where solar heating is weaker and you might expect less thermal activity. Neptune glows with internal warmth. Its primordial heat is escaping exactly as thermodynamic models predict for an ice giant of its age and mass. The pressure cooker is venting. The thermal afterglow is present and measurable. Neptune is doing what the rules say it should do. Neptune is not a perfect textbook planet. Its tilted magnetic field hints at interior complexity that we do not fully understand, but it sits recognizably within the framework. It follows the rules closely enough that scientists can explain its behavior using established physics with only moderate extrapolation. Neptune is the well-behaved sibling, the one who graduated on time, got a respectable job, and calls home on the weekends. Then there is the other one. When Voyager 2 flew past Uranus on the 24th of January, 1986, it was the first and to this day the only spacecraft to visit the seventh planet. The encounter lasted a matter of hours. The spacecraft was travelling at roughly 42,000 miles per hour relative to Uranus, which meant the window for close-range observations was brutally short. Engineers had spent years programming the spacecraft's instruments to collect as much data as possible during the flyby, prioritizing measurements of the atmosphere, the magnetic field, the ring system, and the largest moons. The data that came back did not just surprise the planetary science community, it systematically disassembled every prediction they had made. Scientists already knew about the tilt before Voyager arrived. Ground-based observations stretching back decades had established that Uranus rotates with an axial inclination of approximately 97.8 degrees. The planet does not lean. It has fallen completely onto its side. Its rotation axis points nearly in the plane of its orbit rather than perpendicular to it. No other planet in the solar system comes close to this configuration. This alone was bizarre enough to generate decades of speculation about catastrophic impacts and unusual formation conditions. But the tilt was the anomaly everyone expected to confront. Scientists had prepared models, developed hypotheses, rehearsed explanations. What they were not prepared for was everything else. Voyager 2 measured a magnetic field tilted approximately 60 degrees from the rotation axis and offset from the planet's geometric center by roughly 1/3 of the planet's radius. It detected an atmosphere so calm and featureless that Uranus became visually the most boring planet Voyager had encountered, and it measured thermal emissions suggesting virtually no excess internal heat was escaping. Each measurement was a separate violation. Each violation contradicted a separate prediction, and the violations did not point toward a single, clean explanation. The tilt suggested a catastrophic impact, but an impact should have mixed the interior and produced vigorous heat emission. The quiet atmosphere suggested a thermally inert planet, but the extreme seasonal forcing from the tilt should have driven powerful weather systems. The tilted magnetic field suggested an unusual dynamo configuration, but the offset from the planet's center implied interior conditions that standard models could not account for. Uranus had not just broken one rule, it had broken all of them simultaneously, and the violations contradicted each other in ways that made any single explanation feel incomplete before it was even fully articulated. The scientific community was left with something it does not encounter often. A planet that appeared to be internally consistent in its own bizarre way, but externally inconsistent with every framework ever developed to explain how planets work. This was not a case of one anomalous measurement suggesting an instrument error. This was a coherent body of evidence pointing toward a world that operates under conditions we had never anticipated and still, nearly 4 decades later, cannot fully explain. The rules were clear, the data were clear, and they did not agree. What comes next is the detailed anatomy of each violation measured, documented, and compared against the precise predictions it defied. Every anomaly carries a specific, quantifiable signature. Every signature points toward the event or process that made Uranus what it is today. And every failed explanation brings us closer to a truth that extends far beyond one misfit planet in the outer solar system. Let us begin with the tilt, because the tilt is not just one anomaly. It is a cascade of consequences that ripples through every other property of the planet. We established that Uranus rotates with an axial inclination of approximately 97.8 degrees, but stating the number does not convey what this actually means for a planet trying to function as a planet. This is not a modest lean like Earth's 23-degree tilt that gives us mild seasons and long summer evenings. This is a world lying almost flat on its side relative to its orbital plane, rotating like a chicken on a rotisserie spit as it circles the sun. And the consequences for how the planet receives energy, drives weather, and experiences time itself are unlike anything else in our solar system. Consider what happens during a single orbit. Uranus takes approximately 84 Earth years to complete one trip around the Sun. At the solstice, one pole faces the Sun almost directly. That pole receives continuous sunlight for roughly 42 years without interruption. Meanwhile, the opposite pole sits in complete darkness for the same duration. No sunrise, no sunset. Just 4 decades of unbroken night. Then, as the planet moves along its orbit toward equinox, the geometry shifts. The Sun crosses over the equator, and for a relatively brief period the planet experiences something resembling a conventional day-night cycle, with the Sun rising and setting at the equator roughly every 17 hours as Uranus rotates. Then the cycle reverses, and the other pole gets its turn in the light. No other planet experiences anything remotely like this. Mars has seasons similar in character to Earth's, just longer. Saturn's tilt produces familiar seasonal patterns stretched across its 29-year orbit. Even Pluto, demoted and distant, has a more conventional relationship with sunlight than Uranus does. The 7th planet exists in a seasonal regime that has no parallel, and that regime creates thermal conditions that should have dramatic, observable consequences. Here is the specific prediction. When one hemisphere absorbs solar energy continuously for 42 years, while the other hemisphere radiates heat into the vacuum of space for the same period, you get an enormous temperature gradient between the two halves of the planet. Hot air rises, cold air sinks. Temperature differences drive circulation. This is the fundamental engine behind weather on every planet with an atmosphere. The greater the temperature difference, the more powerful the circulation. Earth's relatively modest 23-degree tilt produces hurricanes, monsoons, and jet streams. Uranus's 98-degree tilt should produce atmospheric chaos on a scale that dwarfs anything in the solar system. It does not. When Voyager 2 arrived at Uranus on the 24th of January, 1986, the spacecraft's cameras captured something planetary scientists found almost impossible to reconcile with the physics. The planet looked blank. A pale blue-green sphere with virtually no visible cloud features, no banding, no storm systems, no atmospheric structure that could be resolved at the scales. Voyager's instruments were designed to detect. Jupiter has its great red spot and vivid alternating bands of coloured clouds. Saturn has its hexagonal polar vortex and creamy butterscotch cloud layers. Neptune, which Voyager would visit 3 years later, turned out to be everything the textbooks predicted and more. Uranus showed almost nothing. To appreciate how wrong this looked, consider that Voyager 2 arrived during the southern summer solstice. The South Pole was aimed almost directly at the Sun and had been baking in continuous sunlight for roughly 2 decades. The North Pole had been in darkness for the same duration. If any moment in the Uranian year should have produced dramatic atmospheric circulation, this was it. Maximum asymmetry, maximum thermal forcing, and the atmosphere responded with what appeared to be profound indifference. Scientists initially questioned whether the bland appearance might be an artifact of the viewing geometry. Voyager approached from the sunlit South Pole, meaning it was looking almost straight down onto the illuminated hemisphere. Perhaps the atmospheric features were there but oriented in ways that made them difficult to image from that angle. Perhaps the interesting weather was confined to the dark hemisphere where the cameras could not reach. The imaging team processed and reprocessed the data, stretching contrast levels and filtering wavelengths to extract any hidden structure. They found very little. A few faint cloud bands at southern latitudes, a handful of small discrete features, nothing remotely approaching the atmospheric drama observed at every other giant planet. Subsequent observations addressed some of these concerns but deepened the mystery in others. As Uranus moved through its orbit toward the northern spring equinox in 2007, Hubble Space Telescope observations began revealing increased atmospheric activity. Bright methane ice clouds appeared in the northern hemisphere as it emerged from decades of darkness into increasing sunlight. Scientists were cautiously encouraged. Perhaps the atmosphere needed seasonal transitions to become active. Perhaps the equinox, with its rapidly changing illumination geometry, was the trigger that solstice conditions could not provide. By 2014, ground-based telescopes using adaptive optics systems at the Keck Observatory in Hawaii detected surprisingly vigorous storm activity at near-infrared wavelengths. A cluster of exceptionally bright features appeared in the northern hemisphere, among the most luminous storm systems ever recorded on the planet. These storms reached altitudes high enough in the atmosphere to punch through the haze layers that normally obscure deeper structures. For a brief period, Uranus looked almost dynamic. Atmospheric scientists were fascinated because the storms arrived years after the equinox, at a point in the seasonal cycle when models predicted declining activity rather than increasing it. The atmosphere was responding to seasonal change, but on its own schedule, out of phase with the solar forcing that should have been driving it. So the atmosphere is not entirely dead. It responds to seasonal changes, but the response is dramatically muted and strangely timed compared to what physics predicts. Neptune, with a conventional tilt and far less extreme seasonal forcing, sustains continuous atmospheric turbulence regardless of its orbital position. Its cloud features evolve on timescales of days and weeks. The most violent sustained winds in the solar system belong to the planet, with less reason to be angry. Neptune's atmosphere behaves like a giant planet's atmosphere should behave. Uranus's atmosphere behaves like something is missing, like the engine that should be driving violent circulation has been disconnected from the machine. The culprit, as we will see, connects directly to the next violation. But before we leave the tilt, there is one more consequence that matters. The extreme axial inclination does not just affect weather patterns. It defines the geometry of everything that orbits the planet. Uranus has 29 known moons and a system of thin, dark rings. Every single one of these objects orbits in the planet's equatorial plane. Because the equator is tilted 98 degrees relative to the orbital plane around the Sun, the entire satellite system appears to orbit vertically when viewed from the perspective of the solar system. The moons do not go around the equator in the conventional sense. They go over the poles relative to the Sun. This co-tilted moon system is not a minor detail. It is an enormously constraining observation for any theory that attempts to explain the tilt. If a sudden event knocked Uranus on its side after the moons had already formed in a conventional equatorial disk, those moons should have been stranded in the original orbital plane. They would not have instantly shifted to the new equatorial plane. Gravitational torques from the planet's oblate shape would eventually drag them into the new plane, but this process takes time and might not capture all the moons cleanly. Some could be lost to unstable orbits. The fact that all 29 known moons orbit neatly in the current tilted equatorial plane constrains how and when the tilting event occurred. Either it happened before the moons formed, or it happened slowly enough for the moons to follow along. Keep that constraint in your mind. It will matter when we investigate causes. Now let us go deeper. Beneath the clouds, beneath the hydrogen and helium envelope, past the point where atmospheric pressure exceeds anything found on Earth's surface by factors of hundreds of thousands, lies the region where Uranus generates its magnetic field. Or rather, where it should generate a normal magnetic field. What it actually generates is something that looked, to the scientists analysing Voyager 2's magnetometer data, like the output of a compass needle dropped into a blender. The expectation was straightforward and well supported by precedent. Giant planets produce magnetic fields through convective dynamos, operating in electrically conducting interior fluids. The rotation of the planet organizes the convection into patterns that generate a field roughly aligned with the spin axis. Jupiter's field tilts 10 degrees from its rotation axis. Saturn's field tilts less than 1 degree. Earth's field tilts about 11 degrees. The pattern is clear and physically motivated. The dynamo respects the spin. The magnetic poles stay near the geographic poles. The magnetometer aboard Voyager 2 began detecting Uranus's magnetic field hours before closest approach, as the spacecraft entered the planet's magnetosphere. The initial readings were confusing. The field did not behave as the approach models predicted. It strengthened in unexpected directions. The polarity seemed wrong for the expected geometry. As the spacecraft flew closer and the data sharpened, the picture that emerged was unlike anything previously measured at any planet. Uranus's magnetic field is tilted approximately 59 degrees from the rotation axis. This is not a modest offset. This is a magnetic field, whose poles are located closer to the equator than to the geographic poles. If you stood on Uranus at the geographic North Pole and held a compass, the needle would not point down toward your feet the way it roughly does on Earth. It would point off at a steep angle toward the horizon, directing you toward a location far from where any theory says the magnetic pole should be. But the tilt was only half the shock. The magnetic field's center of symmetry does not coincide with the planet's geometric center. It is offset by approximately 1/3 of the planet's radius, displaced toward the southern rotational pole. A magnetic field is usually modeled as though it were generated by a dipole, essentially a bar magnet, located at the center of the planet. For Jupiter and Saturn, this approximation works well. The dipole sits near the center, the field is roughly symmetric, and the higher-order components are small corrections. For Uranus, the dipole is not at the center. It is shifted dramatically to one side, producing a magnetic field that is wildly asymmetric at the surface. The field strength varies by more than a factor of 10 between different locations on the planet, far more than any other measured planetary field. The scientists who first processed these measurements at the Jet Propulsion Laboratory in Pasadena faced an uncomfortable situation. The data were clean, the instruments were functioning correctly. Multiple independent measurements during the flyby confirmed the same bizarre geometry. Norman Ness, who led the magnetometer team, described the result as fundamentally unexpected. The field did not match any of the pre-encounter models the team had prepared. They had considered the possibility of a modestly tilted field, perhaps 15 or 20 degrees. They had not prepared for 59 degrees. Nobody had, because no physical model predicted it. The combination of extreme tilt and large offset creates a magnetosphere, the region of space controlled by the planet's magnetic field that is unlike anything else in the solar system. As Uranus rotates, its tilted offset magnetic field wobbles through space in a corkscrew pattern. The magnetosphere does not sit neatly around the planet like Jupiter's does. It tumbles, creating a constantly shifting interaction with the solar wind that produces complex and rapidly changing auroral patterns. The geometry is so unusual that modeling it requires abandoning many of the simplifying assumptions that work perfectly for every other magnetized planet. At certain rotational phases, the magnetic tail stretches out behind the planet in a configuration that is almost perpendicular to the solar wind flow. A quarter rotation later, the tail is twisted into a completely different orientation. The magnetosphere of Uranus does not just differ from Jupiter's in degree, it differs in kind. When the Voyager team first reported these measurements, a natural objection arose. Perhaps the spacecraft had caught Uranus in the middle of a magnetic field reversal. Earth's magnetic field reverses polarity every few 100,000 years on average, and during the transition the field becomes chaotic, weakened, and multipolar. If Uranus happened to be reversing its field during the 1986 flyby, the bizarre measurements might represent a temporary transitional state rather than the planet's normal operating condition. This objection was reasonable for about 3 years. Then Voyager 2 flew past Neptune in 1989, and measured a magnetic field that was similarly tilted, approximately 47 degrees from the rotation axis, and similarly offset, displaced from the planet's center by about 55% of Neptune's radius. The probability of both ice giants coincidentally undergoing magnetic reversals at the exact same time Voyager happened to fly by is vanishingly small. The far more compelling conclusion was that tilted offset magnetic fields are the normal configuration for ice giant dynamos. Something about the internal structure of these planets produces this geometry as a permanent feature, not a temporary aberration. The reversal hypothesis was effectively dead. This conclusion has profound implications for interior structure. The geometry of a magnetic field is determined by the geometry of the conducting region that generates it. In Jupiter and Saturn, the dynamo operates deep in the planet where metallic hydrogen provides a large, roughly spherical conducting volume. A deep spherical dynamo naturally produces a dipole field aligned with the rotation axis. The physics and the observations agree. In Uranus, the tilted offset field suggests the dynamo does not operate deep in the core. Instead, it may be confined to a relatively thin shell of electrically conducting fluid at intermediate depths. Water, ammonia, and methane compressed to extreme pressures become ionic conductors, fluids where dissolved molecules dissociate into charged particles that can carry electrical current. If convection is restricted to a narrow zone within this conducting layer, rather than extending throughout the interior, the resulting dynamo operates in a thin shell, rather than a thick sphere. Shell dynamos produce inherently more complex fields with larger tilts and offsets, because the geometry of the generating region is fundamentally different. A thin shell cannot sustain the same organized flow patterns that a deep spherical volume can. The convection is more chaotic, the field more disordered, and the resulting dipole component ends up tilted far from the rotation axis. Computer simulations confirm that thin shell dynamos can reproduce the magnetic field configurations observed at both Uranus and Neptune with reasonable accuracy. But this explanation immediately raises the question of why convection would be confined to a thin shell. In a well-mixed interior where heat flows freely from the core to the surface, convection should extend through the entire conducting region. Something must be blocking the convection from reaching the deep interior. Something must be creating a barrier that confines the dynamo to a shallow layer. And that barrier connects directly to the most thermally puzzling observation in the entire solar system. Uranus emits almost no excess internal heat. This is the third violation, and in many ways it is the most difficult to explain because it contradicts one of the most robust predictions in planetary physics. Giant planets form hot. Gravitational contraction converts potential energy to thermal energy, heating the interior to tens of thousands of degrees. That heat must escape eventually, but the timescale for a planet the size of Uranus to fully cool is far longer than the current age of the solar system. 4.5 billion years is simply not enough time. The planet should still be warm, the heat should still be leaking out. We have already seen that Jupiter, Saturn, and Neptune all radiate far more heat than the Sun delivers to them. Neptune glows with internal warmth, exactly as thermodynamic models predict for an ice giant of its age and mass. Uranus emits at most 1.06 times the energy it receives from the Sun. Some measurements are consistent with an excess of exactly 0. The planet appears to be in near-perfect thermal equilibrium with its environment, radiating away almost precisely what the Sun puts in, and nothing more. For a 14.5 Earth mass world that formed through gravitational collapse 4.5 billion years ago, this is not just unexpected. It borders on physically implausible, unless something specific is preventing the heat from escaping. The contrast with Neptune demolishes any attempt to explain this through normal cooling. Neptune is only 17% more massive than Uranus. They are believed to share broadly similar compositions and formation histories. If normal thermal evolution applied equally to both planets, their heat outputs should be comparable. They are not. Neptune radiates vigorous excess heat. Uranus radiates essentially nothing. Whatever silenced the thermal emission of the 7th planet did not touch the 8th. Two near-twin worlds, one glowing, One dark, same size, same materials, same age, completely different thermal behavior. That contrast alone tells scientists that something specific happened to Uranus, something that did not happen to Neptune, that fundamentally altered how heat moves through its interior. The most compelling explanation is interior stratification. Imagine the planet's interior is not well mixed, but instead organized into layers of different composition and density. A dense layer sitting beneath a lighter layer creates a stable configuration that resists convective overturning. Hot material at the bottom cannot rise through the denser layer above. Cold material at the top cannot sink through the lighter layer below. Convection, the most efficient mechanism for transporting heat from a planet's interior to its surface, is effectively shut down across the boundary. Heat trapped below this compositional barrier can only escape through thermal conduction, which is orders of magnitude slower than convection. Think of it like a thermos flask with the lid screwed on too tight. The heat is inside, the insulation is working. The contents stay warm for far longer than they would in an open container. Uranus's interior may still be scorching hot at depth, retaining most of its primordial formation energy behind a compositional wall that prevents it from reaching the surface. The planet is not cold, it is insulated. The heat is there, it simply cannot get out. This model elegantly connects two of the violations. A stably stratified interior explains both the missing heat and the shell dynamo. Convection is confined to a thin layer above the compositional boundary, producing the tilted offset magnetic field. Heat below the boundary escapes slowly through conduction, producing the near-zero thermal excess measured at the surface. Two apparently separate anomalies turn out to be different symptoms of the same underlying condition, but it also connects to the muted atmosphere. If very little internal heat reaches the upper atmosphere, the energy available to drive atmospheric circulation is drastically reduced compared to a planet like Neptune, where internal heat flows freely to the surface. The atmospheric engine is starved of fuel. Weather systems that should be vigorous and visually spectacular become sluggish and subdued. The bland, featureless disk that Voyager 2 photographed is not evidence of a boring planet. It is evidence of a planet whose internal plumbing has been fundamentally altered, cutting off the energy supply that should power visible atmospheric dynamics. There is a fourth element that compounds the puzzle. Spectroscopic observations of Uranus's atmosphere reveal that its composition is broadly similar to Neptune's at the level of bulk chemistry. Both planets have hydrogen-helium atmospheres enriched with methane at concentrations of roughly 2 to 3%. Both owe their blue colors to that methane, but despite this chemical similarity, the two planets look strikingly different. Neptune appears as a vivid, deep blue world with visible cloud bands, discrete storm features, and an atmosphere that changes noticeably over timescales of days. Uranus appears as a washed-out, pale blue-green sphere with a hazy, featureless quality that makes it look almost airbrushed. The difference is not chemical composition but vertical atmospheric structure. Uranus has a significantly thicker haze layer in its upper atmosphere compared to Neptune. This photochemical smog, produced by ultraviolet sunlight breaking apart methane molecules into more complex hydrocarbons, forms a semi-opaque blanket that obscures deeper cloud features from view. Why Uranus produces a thicker haze than Neptune is not fully understood, but it likely connects to the thermal profile of the atmosphere. Without significant internal heat warming the atmosphere from below, Uranus's temperature structure is different from Neptune's. The tropopause, the boundary between the lower and upper atmosphere, sits at a different altitude and temperature. This affects where hazes form, how quickly they settle, and how thick they accumulate. The missing internal heat does not just reduce atmospheric vigor, it changes the chemistry of what we can see, wrapping the planet in a translucent veil that makes it appear calm, even if dynamic processes are occurring at deeper, hidden levels. Recent observations support this interpretation. When astronomers observe Uranus at near-infrared wavelengths that penetrate below the upper haze layers, they find more atmospheric structure than visible light images reveal. Discrete cloud features, bright methane ice storms, and even hints of banded structure appear at wavelengths where the haze becomes more transparent. The atmosphere is not as dead as Voyager's visible light cameras suggested. It is partially alive, but hidden beneath a fog of its own making. A fog that exists because the interior heat that should keep the atmosphere energetically active is locked away behind a compositional barrier deep below. Every violation reinforces the others. The tilt creates extreme seasonal forcing. The missing heat removes the internal energy that should amplify atmospheric response to that forcing. The stratified interior that traps the heat also confines the dynamo to a thin shell, producing the tilted offset magnetic field. The reduced heat flux alters the atmospheric temperature profile, producing thicker hazes that obscure whatever weather does exist. The co-tilted moon system constrains the timeline and mechanism of whatever event created this configuration. These are not 5 separate mysteries. They are 5 manifestations of one mystery. Something happened to Uranus, probably early in the solar system's history, that restructured its interior in a way that differs fundamentally from what happened to Neptune or any other planet. That single event or process set in motion a chain of consequences that affected the planet's rotation, its magnetic field, its thermal evolution, its atmospheric dynamics, and its satellite systems simultaneously. The question of what that event was has consumed planetary scientists for nearly 4 decades. The leading hypotheses differ dramatically in their assumptions, their predictions, and their implications for how common Uranus-like planets might be throughout the galaxy. Each hypothesis explains some of the violations convincingly while struggling with others. None of them, as of today, explains everything. But the fact that the violations are interconnected is itself a powerful constraint. Any successful theory must account for all 5 simultaneously. You cannot explain the tilt without addressing the heat. You cannot address the heat without explaining the magnetic field. You cannot explain the magnetic field without understanding the interior structure, and you cannot understand the interior structure without knowing what event created it. The investigation into what broke Uranus is not a collection of separate research programs running in parallel. It is a single, unified puzzle where every piece constrains every other piece. What follows is an examination of the leading theories, one by one, testing each against the full weight of observational evidence to see which ones survive and which ones collapse under the burden of a planet that refuses to be explained by any simple answer. Something happened to Uranus. We have established what the damage looks like. A planet on its side, a magnetic field pointing the wrong way, an interior hoarding heat it should have released billions of years ago, an atmosphere too quiet for the extreme seasonal punishment it endures, a moon system that tilted along with the planet. 5 connected violations, 5 symptoms of a single underlying event. Now comes the harder question. What event could produce all of this simultaneously? The investigation has been running for nearly 4 decades, and it has generated 3 major families of hypotheses. Each one starts from a different physical mechanism. Each one explains some of the evidence convincingly, and each one struggles with at least one piece of evidence that refuses to cooperate. This is the current state of the science, not a solved case with a neat conclusion, but an active investigation with multiple suspects, partial alibis, and no confession. Let us start with the most dramatic hypothesis, because it was proposed first and remains the most widely discussed: a giant impact. Early in the solar system's history, during the violent final stages of planetary assembly, a massive object slammed into the young Uranus and knocked it onto its side. The impactor was not a small asteroid or a stray comet. It was a protoplanetary body, a partially formed world, with a mass estimated between 1 and 3 times the mass of Earth. An object that large colliding with Uranus at orbital velocities would deliver enough angular momentum to tip the planet's rotation axis from a modest initial tilt to the 98 degrees we observe today. This hypothesis has strong historical precedent. Giant impacts are not exotic or speculative events. They are a confirmed and expected feature of the late stages of solar system formation. The leading theory for the origin of Earth's moon involves a Mars-sized body striking the young Earth and ejecting a cloud of debris that coalesced into our lunar companion. Mercury's anomalously large iron core may reflect a giant impact that stripped away much of its rocky mantle. Venus's slow retrograde rotation might also trace back to a massive collision early in its history. Giant impacts shaped the early solar system repeatedly, violently, and without regard for the neat geometries that the original protoplanetary disk tried to impose. Invoking one to explain Uranus is not a stretch. It is almost conservative. Computer simulations of the impact scenario have grown increasingly sophisticated over the decades. Researchers model the collision using smoothed particle hydrodynamics, a computational technique that represents both the planet and the impactor as collections of thousands to millions of individual particles, each carrying properties like mass, temperature, density, and composition. The simulation tracks what happens when these particle collections collide at various angles and speeds, following the debris, energy transfer, and angular momentum redistribution in 3 dimensions over hours to days of simulated time. The parameter space is large. You can vary the impactor's mass, its composition, its velocity, the angle at which it strikes, and the initial conditions of the young Uranus before impact. Researchers have explored hundreds of combinations searching for scenarios that reproduce the observed tilt while keeping the planet intact. The results consistently identify a sweet spot. A grazing impact works far better than a head-on collision. Think of a snooker ball clipping another at speed rather than striking it dead center. A grazing blow transfers angular momentum efficiently because the impactor's velocity has a large component tangent to the planet's surface. It tips the planet without delivering so much energy to the core that the entire world is disrupted or, in extreme cases, partially destroyed. The best-fit scenarios use an impactor of roughly 1 to 2 Earth masses striking at an angle between 45 and 75 degrees relative to the planet's surface. These collisions successfully reproduce the 98-degree tilt in a single event. They also generate a disk of debris around the newly tilted planet, material blown off from both the impactor and Uranus's outer layers that settles into orbit in the new equatorial plane. This debris disk could, over thousands to millions of years, coalesce into the regular satellite system we observe today. The moons would form in the tilted plane because the disk itself would damp into that plane through mutual collisions and gravitational interactions. The rings might represent debris that remain too close to the planet to accrete into larger bodies, held apart by tidal forces that prevent consolidation. So far, so good. The single giant impact explains the tilt and provides a natural mechanism for the co-tilted moons. But the moment you ask what happens to the planet's interior, the model runs into trouble. A collision energetic enough to tilt a 14.5 Earth mass planet by 98 degrees deposits an enormous amount of thermal energy into the interior. The impact heats the outer layers to thousands of degrees. Shockwaves propagate through the planet, stirring and mixing material that was previously stratified. The interior should end up thoroughly homogenized, a well-mixed soup of rock, ice, and gas with no sharp compositional boundaries, and a well-mixed interior convects freely. Heat from the deep core travels efficiently to the surface. The planet should glow with thermal energy for billions of years afterward. This is precisely what we do not observe. But as we have seen, the planet's thermal output tells a completely different story. The interior appears to be stably stratified, with suppressed convection trapping heat at depth. A single catastrophic impact that mixed the interior should have produced the opposite outcome. More heat escaping, not less. Stronger convection, not weaker. A deep dynamo producing an aligned magnetic field, not a shell dynamo producing a tilted offset one. Let us put this in the form of a scoreboard. The single giant impact hypothesis scores a clear win on the tilt. It scores a plausible win on the co-tilted moons through the debris disk mechanism. It scores a clear loss on the missing heat, and it scores a likely loss on the magnetic field, because a well-mixed interior should produce a deep dynamo rather than a shell dynamo. 2 wins, 2 losses, not good enough to close the case. This contradiction drove researchers toward a modified version of the hypothesis. What if the impact did not fully mix the interior? Recent high-resolution simulations, run with far more particles and better treatment of material properties than earlier work, suggest this is possible under specific conditions. A grazing impact deposits most of its energy into the outer layers of the planet while leaving the deep interior relatively undisturbed. The impactor itself, if it had a different composition from Uranus's core, could contribute material that settles into a boundary layer at intermediate depths. This compositional boundary would resist convective overturning, creating exactly the kind of stable stratification needed to explain the trapped heat and the shell dynamo. The scenario works like this. Before the impact, young Uranus has a partially differentiated interior with a rocky core, an icy mantle, and a hydrogen-helium envelope. The impactor strikes at a grazing angle, heating and disrupting the outer envelope and the upper portion of the icy mantle. Material from the impactor, which may be richer in rock and iron than the surrounding ice, mixes into the upper mantle and settles into a dense transitional layer. Below this layer, the original deep interior remains largely intact, still hot from formation, but now insulated by a compositional barrier it cannot convect through. Above the barrier, a thinner layer of conducting ice-rich fluid convects normally, producing the shell dynamo responsible for the tilted magnetic field. The revised scoreboard for this modified impact model looks better. The tilt is still explained. The moons are still explained. The missing heat is now explained through the stratification created by impactor material settling into a boundary layer. The magnetic field geometry is explained by the resulting shell dynamo. 4 potential winds. But every win comes with an asterisk. The angle must be grazing enough to avoid fully mixing the interior. The impactor's composition must differ from Uranus's bulk composition in a way that creates a stable density gradient. The energy deposition must be concentrated in the outer layers while sparing the deep core. These requirements narrow the window of acceptable collisions significantly. The hypothesis works, but only if nature hit a fairly specific bullseye. The multiple impact hypothesis relaxes some of these constraints at the cost of introducing others. Instead of one massive collision, perhaps Uranus was tipped by a series of smaller impacts spread over millions of years during the late stages of accretion. 2 or 3 bodies, each a fraction of an Earth mass, striking at different times and from different directions, could cumulatively build up the tilt to 98 degrees without any single event, delivering enough energy to fully homogenize the interior. Each impact would heat and mix a portion of the planet, but the intervals between impacts would allow partial cooling and restratification. The final configuration would be a planet with a large tilt and a partially stratified interior, both achieved incrementally. Simulations of the multiple impact scenario are computationally expensive because each collision must be modeled separately, and the planet must be allowed to thermally and dynamically relax between events. Early results suggest the approach is viable. Multiple moderate impacts can reproduce the observed tilt while preserving more internal stratification than a single large impact. However, there is a statistical problem. For the cumulative tilt to reach 98 degrees, the successive impacts need to push the axis predominantly in the same direction. Random impacts from random directions would tend to cancel each other out, sometimes tilting the planet further and sometimes tilting it back. Getting a net tilt of 98 degrees from multiple random collisions requires either a fortunate alignment of impact geometries or a larger number of impacts to ensure the random walk in tilt space reaches the observed value. This is not impossible, but it is less probable than a single well-aimed blow. Each additional impact adds a free parameter to the model, making it more flexible but also more difficult to constrain observationally. Some researchers view the flexibility as an advantage because it allows the model to accommodate a wider range of interior outcomes. Others view it as a weakness because a model that can explain almost anything predicts almost nothing. The second family of hypotheses does not involve impacts at all. It proposes that Uranus was tilted gradually through gravitational interactions during the early solar system's orbital reshuffling. This requires some context about what the early solar system looked like, because it was dramatically different from what we see today. The standard model of early solar system evolution, often called the Nice model, after the French city where it was developed, proposes that the 4 giant planets formed in a much more compact configuration than their current orbits. Jupiter, Saturn, Uranus, and Neptune all orbited closer to the Sun and closer to each other, with orbital spacings far tighter than the vast gulfs that separate them now. Beyond the outermost planet lay a massive disk of icy planetesimals, leftover building material containing perhaps 35 Earth masses of rock and ice that had not been incorporated into any planet during the accretion phase. For hundreds of millions of years, this configuration remained roughly stable. The planets interacted gravitationally with the planetesimal disk, slowly exchanging angular momentum. Neptune drifted outward into the disk, scattering planetesimals inward, where they encountered Uranus, then Saturn, then Jupiter. Jupiter, being the most massive, flung most of these small bodies outward, transferring orbital energy to the outer planets and causing them to migrate further from the Sun. This slow migration proceeded gradually until a critical threshold was crossed. Jupiter and Saturn drifted into a mutual orbital resonance, a configuration where Jupiter completed exactly 2 orbits for every 1 orbit of Saturn. This resonance amplified their gravitational interactions explosively, destabilizing the entire outer solar system in a period of chaos lasting perhaps 50 to 100 million years. During this instability, everything moved. Uranus and Neptune were scattered onto highly eccentric, inclined orbits. In many simulations, the 2 ice giants pass close enough to each other to exchange positions entirely. Neptune, currently the outermost planet, may have originally formed closer to the Sun than Uranus. The gravitational encounters during this period were violent enough to fling both planets onto wild trajectories before friction from the remaining planetesimal disk gradually circularized their orbits into the nearly circular paths we observe today. If you picture the planet's orbits as furniture in a room, the Nice model instability was the event where someone rearranged everything while you were out. Nothing ended up where it started, and some of it got knocked around badly in the process. Migration alone does not produce the extreme tilt of Uranus. Gravitational scattering between planets can change orbital parameters dramatically, but typically does not alter spin axes by more than a few tens of degrees. However, migration changes the orbital architecture, which changes the gravitational torques acting on each planet's spin axis. If Uranus passed through a spin-orbit resonance during migration, its tilt could have been amplified gradually over millions of years. A spin-orbit resonance occurs when the rate at which a planet's spin axis precesses, the slow wobble of the axis around a reference direction, matches the rate at which its orbit precesses due to gravitational perturbations from other planets. When these 2 frequencies match, energy is transferred resonantly into the planet's obliquity, pumping up the tilt in the same way that pushing a child on a swing at just the right frequency builds up larger and larger oscillations. Under the right conditions, a spin-orbit resonance can drive a planet's tilt from modest values to extreme ones over timescales of millions of years. Recent theoretical work has identified specific scenarios where this mechanism could tilt Uranus to 98 degrees. The key ingredient is a large circumplanetary disk around the young Uranus, a disk of gas and debris left over from the planet's formation that had not yet dissipated or accreted onto the planet. This disk changes the planet's precession rate, potentially bringing it into resonance with an orbital frequency driven by interactions with other migrating planets. As the disk slowly disperses over millions of years, the resonance sweeps through different frequencies, and if the timing is right, it can capture and amplify the tilt before releasing it at a high value. The gradual tilting mechanism has an appealing feature that the impact hypothesis struggles with. Because the tilt increases slowly over millions of years, the planet's moons have time to track the changing equatorial plane through tidal interactions with the planet's oblateness. The moons are not stranded in an old orbital plane by a sudden violent event. They are dragged along gently, maintaining their equatorial orbits as the equator itself shifts. This naturally explains the co-tilted satellite system without requiring the moons to reform from an impact-generated debris disk. Running the scoreboard on the resonant tilting hypothesis gives a different pattern. Tilt explained, yes. Co-tilted moons explained, arguably better than the impact model. Missing heat, no explanation offered. Magnetic field geometry, no explanation offered. Atmospheric quiescence, no explanation offered. 2 wins, 3 blanks. The hypothesis does not contradict the interior anomalies, but it does not address them either. They become orphaned mysteries requiring their own separate solutions, which reduces the elegance of the overall explanation considerably. Some researchers have proposed hybrid models where a gradual resonant tilt is supplemented by one or more moderate impacts that restructure the interior without fully determining the final tilt. The resonance does the heavy lifting on obliquity while the impact handles the interior stratification. This approach is physically plausible but introduces additional complexity and free parameters. The more mechanisms you combine, the harder it becomes to test the model against observations because the predictions become less specific. The third investigative thread turns inward, literally, to the question of what Uranus is made of at depths no instrument has ever directly sampled. Our understanding of ice giant interiors is built almost entirely on indirect evidence. Mass and radius measurements constrain the bulk density. Gravitational field measurements from Voyager 2's flyby constrain the distribution of mass at coarse resolution. Magnetic field measurements constrain where electrically conducting fluids exist. Atmospheric spectroscopy constrains the composition of the outermost layers. Everything deeper than the cloud tops is modelled, not measured. The standard 3-layer picture we established earlier, a rocky core beneath a compressed icy mantle beneath a hydrogen-helium envelope, is almost certainly an oversimplification. The real interior probably involves gradual compositional transitions rather than sharp boundaries, and the behavior of materials under the relevant pressures and temperatures is only beginning to be explored in laboratory settings. This is where the science gets genuinely strange, and where experiments conducted on Earth start to feel like science fiction. Laboratory physicists have developed techniques for recreating the pressures and temperatures found deep inside ice giants, not in large volumes, but in microscopic samples squeezed between the tips of 2 gem-quality diamonds. These diamond anvil cells compress tiny samples of water, ammonia, or methane to pressures exceeding millions of atmospheres, while high-powered lasers simultaneously heat them to thousands of degrees. The samples are smaller than a grain of sand and survive in these extreme states for only fractions of a second. But that is long enough for X-ray diffraction instruments to determine what the material's atomic structure looks like under those conditions. It is like squeezing a walnut until it cracks and discovering something completely unexpected inside. What these experiments revealed about water under ice giant interior conditions shocked the materials science community. At pressures exceeding roughly 200,000 atmospheres and temperatures of several thousand degrees, water enters a phase called superionic ice. In this state, the oxygen atoms lock into a rigid crystalline lattice, forming a solid framework. Meanwhile, the hydrogen atoms, stripped of their electrons by the extreme conditions, flow freely through this lattice like a liquid. The material is simultaneously solid and liquid depending on which atomic species you are tracking. The oxygen scaffold is frozen in place. The hydrogen flows through it like water through a pipe. This dual nature gives superionic water extraordinary properties. It conducts electricity efficiently because the mobile hydrogen ions carry charge through the lattice, but its thermal transport properties differ dramatically from those of a normal convecting fluid. The rigid oxygen lattice resists the bulk fluid motions that characterize convection. Heat cannot be carried upward by rising plumes of hot material because the solid framework prevents large-scale overturning. Instead, heat must conduct through the lattice atom by atom, a process that is orders of magnitude slower than convective transport. Superionic water was confirmed experimentally in 2018 by a team using the National Ignition Facility's laser system at Lawrence Livermore National Laboratory. The researchers compressed a thin layer of water between diamond anvils to pressures matching those expected roughly halfway between Uranus's surface and its core, then used powerful laser pulses to heat the sample while simultaneously probing its structure with X-ray diffraction. The results were unambiguous. Water at those conditions formed a superionic phase with the predicted crystal structure. The exotic state of matter that theorists had speculated about for decades was real, and it existed at precisely the conditions found inside ice giant planets. If a layer of superionic ice exists at intermediate depths inside Uranus, it could act as a physical barrier to convection. Heat would be forced to travel through this layer by conduction rather than convection, dramatically slowing the rate at which primordial energy escapes from the deep interior to the surface. The conducting fluid above the superionic layer would be the only region free to convect, confining the dynamo to exactly the kind of thin shell that reproduces the Voyager measurements. One physical mechanism, rooted in the fundamental behavior of water under extreme compression, would simultaneously explain both the trapped heat and the magnetic field geometry. The scoreboard for the superionic ice hypothesis looks different again. Tilt, no explanation offered. Co-tilted moons, no explanation offered. Missing heat, strongly explained. Magnetic field geometry, strongly explained. Atmospheric quiescence, explained as a downstream consequence of the heat trapping. 2 blanks but 3 wins, and the wins address the anomalies that the impact and resonance models struggle with most. However, the superionic ice hypothesis raises its own critical question. If the layer forms naturally based on pressure and temperature conditions, why does Neptune not have the same barrier? Neptune is slightly more massive, meaning pressures at comparable depths are slightly higher. The superionic phase should exist in Neptune's interior as well. Yet Neptune convects vigorously and radiates strong internal heat, suggesting either the superionic layer does not form there, or it does not suppress convection as effectively. One possible resolution involves temperature. Neptune's interior may be hotter than Uranus's at the depths where the superionic transition occurs. If the temperature exceeds the stability range of the superionic crystalline phase, the water remains in a fully fluid ionic state that convects normally. The temperature difference between the two planets at a specific critical depth could determine whether a convective barrier forms or not. And that temperature difference might trace back to a difference in formation history, accretion rate, or an ancient impact that deposited extra heat in one planet but not the other. The investigation circles back on itself. The impact hypothesis needs interior stratification to explain the trapped heat, but struggles to preserve stratification through a violent collision. The superionic ice hypothesis provides a natural stratification mechanism, but cannot explain why it operates in Uranus and not Neptune, without invoking some difference in thermal history that might itself require an impact. The resonant tilting hypothesis explains the obliquity and the co-tilted moons gracefully but has nothing to say about the interior anomalies. No single hypothesis survives contact with all the evidence. The giant impact explains the tilt and can, under carefully chosen conditions, produce the right kind of interior stratification, but it requires specific collision parameters that reduce its probability. The resonant mechanism explains the tilt and the moons without violence, but leaves the interior mysteries orphaned. The superionic ice barrier explains the heat trapping and the magnetic field, but needs a reason to operate differently from Neptune, which loops back to requiring some distinguishing event in Uranus's past. The honest conclusion is that we are probably looking at a combination, an impact that occurred within the context of planetary migration, depositing energy and material that altered the thermal profile at the exact depth where superionic water transitions determine whether a convective barrier forms or not. The tilt might have been partially established by the impact and partially amplified by a subsequent spin-orbit resonance. The interior stratification might be partially primordial and partially impact-enhanced. The truth is likely messier than any single clean narrative, which is uncomfortable for scientists who prefer elegant, unified explanations, but entirely consistent with how nature actually operates. What we need, more than anything, is data. The entire investigation has been built on 6 hours of Voyager, 2 observations from 1986, supplemented by ground-based and space telescope observations that can only sample the atmosphere and outermost layers. The gravitational field has been measured at low resolution from a single flyby trajectory. The magnetic field has been sampled along one path through the magnetosphere. The interior remains almost entirely unconstrained by direct observation. Every competing hypothesis makes specific, testable predictions about what a dedicated orbital mission would find. The impact model predicts specific signatures in the gravitational harmonics that reveal the depth and sharpness of compositional boundaries. The resonant model predicts a smoother interior without the sharp layering that impact models produce. The superionic ice model predicts a specific relationship between the magnetic field geometry and the depth at which the conducting shell operates. These predictions differ in measurable ways. They can be distinguished by the right instruments, but only with the kind of sustained, high-precision measurements that an orbiter can provide and a flyby cannot. The investigation is not stalled because scientists have run out of ideas. It is stalled because they have run out of data. The hypotheses are ready. The simulations are waiting. The laboratory experiments have revealed the exotic physics that might govern conditions deep inside the planet. What remains is the single most important step in the entire scientific process. Going there, measuring what is actually happening, and letting the planet itself settle the argument. That mission has been endorsed as the highest priority in planetary science. Its scientific case is built on everything this investigation has uncovered, and its implications extend far beyond one tilted, thermally silent, magnetically confused world in the outer reaches of our solar system. Because understanding what happened to Uranus is not just about solving a local mystery, it is about decoding the most common type of planet in the galaxy. Everything we have discussed so far, the violations, the hypotheses, the exotic interior physics, might sound like an interesting but ultimately local problem. One strange planet in our own backyard behaving badly. Fascinating for specialists, perhaps, but not the kind of discovery that reshapes how we understand the universe. This is where that assumption collapses completely, because the single most important fact about Uranus has nothing to do with its tilt, its magnetic field, or its missing heat. It has to do with what is orbiting other stars. When the Kepler Space Telescope completed its primary mission in 2013, it had identified thousands of confirmed and candidate exoplanets by detecting the tiny dips in starlight caused when a planet crosses the face of its host star. The statistical analysis of this dataset produced one of the most consequential results in modern astronomy. The most common type of planet in our galaxy is not a gas giant like Jupiter. It is not a rocky world like Earth. It is a planet with a radius between approximately 2 and 4 times Earth's radius, a size range that maps directly onto the ice giant category occupied by Uranus and Neptune. These worlds are everywhere. They orbit roughly 1 in 3 sun-like stars, extrapolate across the estimated 400 billion stars in the Milky Way, and you arrive at a staggering conclusion. There may be over 100 billion ice giant-sized planets in our galaxy alone. They outnumber gas giants by a wide margin. They outnumber Earth-sized rocky planets in many stellar environments. They are, by a considerable measure, the default outcome of planet formation. The universe makes ice giants more readily than it makes anything else, and we do not understand them. We have exactly 2 ice giants available for detailed study: Uranus and Neptune. One of them is so anomalous that it breaks every model we build. The other has been visited by a single spacecraft for a few hours and observed at distance ever since. Our entire understanding of the most common type of planet in the galaxy rests on 2 data points, one of which is an outlier. Trying to understand the population of ice giant exoplanets from this foundation is like trying to understand how cars work when the only 2 you have ever opened the bonnet of are both broken in different ways. You can identify parts, you can guess at function, but you cannot claim to understand the engineering. This knowledge deficit is not abstract. It has immediate, practical consequences for how we interpret real observations of real exoplanets being made by real telescopes right now. Consider some of the worlds we have already found. GJ3470b orbits a red dwarf star roughly 12.5 light-years from Earth. It has a mass of approximately 13 Earth masses and a radius suggesting it falls squarely in the sub-Neptune category. Its density indicates a composition that likely includes a significant fraction of water and other volatile ices beneath a hydrogen-rich atmosphere. In many respects, it looks like a smaller Uranus, but we have no way to determine whether its interior is well mixed or stratified. We cannot measure whether its magnetic field is dipolar or chaotically multipolar. We do not know whether it radiates excess internal heat or traps it behind a compositional boundary. Every structural inference we make about this world depends on interior models calibrated against Uranus and Neptune, the very models that Uranus's anomalies call into question. HAPI-11b is a Neptune mass exoplanet orbiting a star roughly 120 light-years away. The Hubble Space Telescope detected water vapor in its atmosphere, making it one of the first sub-Neptune worlds with a confirmed atmospheric detection. Scientists used interior structure models to estimate how much of the planet's mass is atmospheric hydrogen versus deep water and rock. Those estimates depend on assumptions about how water behaves under extreme pressures inside ice giants. If superionic ice phases are common at certain depths, the relationship between bulk water content and observable atmospheric properties changes. The water vapor Hubble detected might represent a different fraction of the planet's total water inventory than current models predict. K2-18b made headlines in 2019 when researchers detected water vapor in the atmosphere of a planet orbiting within its star's habitable zone. The planet has approximately 8.5 times Earth's mass, placing it in the sub-Neptune range. Some scientists proposed it could be a habitable ocean world, with liquid water beneath a hydrogen atmosphere. Others argued it was more likely a mini-Neptune with no solid surface, where the water vapor exists in a deep, hot atmospheric layer incompatible with life. The disagreement comes down to interior structure. Is the planet's interior well mixed with hydrogen extending deep into a fluid water layer? Or is there a sharp boundary between a hydrogen envelope and a water-rich interior, creating the possibility of a liquid ocean at the interface? These are exactly the kinds of structural questions that Uranus's anomalies bear on directly. If stable stratification is common in ice giant interiors, the sharp boundary scenario becomes more plausible. If well-mixed interiors are the norm, the ocean hypothesis fades. Each of these worlds is being interpreted through models built on foundations we know are shaky. It is like building a house on ground you have never inspected and hoping the foundations hold. They might. But Uranus is the giant crack in the basement telling you that the geology underneath is not what you assumed. When astronomers measure the mass and radius of a sub-Neptune exoplanet, those two numbers are often all they have. Mass comes from radial velocity measurements or transit timing variations. Radius comes from the depth of the transit dip. From these two values, scientists calculate the planet's bulk density and then attempt to infer its internal composition. Is it a rocky world with a thick hydrogen atmosphere, a water world with a steam envelope, an ice giant with a mixed interior of compressed volatiles? The answer depends entirely on interior structure models, and those models are calibrated against the only ice giants we can study in detail. If our models of Uranus's interior are wrong, every inference we draw about sub-Neptune exoplanets inherits that error. When a researcher concludes that a distant planet with a density of 1.5 grams per cubic centimeter must have a hydrogen envelope comprising 15% of its total mass, that conclusion flows from assumptions about how hydrogen, water, ammonia, and methane arrange themselves inside a planet of that size. Those assumptions come from interior models built on our understanding of Uranus and Neptune. If stable stratification, superionic ice barriers, and confined convection zones are common features of ice giant interiors rather than unique quirks of one anomalous planet, then the density to composition mapping we currently use could be systematically wrong for billions of worlds. the magnetic field problem carries equally serious implications. Planetary magnetic fields are not just interesting features for magnetometer enthusiasts, they are shields. A strong, coherent magnetic field deflects the charged particles streaming outward from a host star, particles that would otherwise strip away atmospheric gases through a process called sputtering. Over billions of years, a planet without magnetic protection can lose a significant fraction of its atmosphere, potentially transforming a world that could have supported life into a barren rock. When scientists evaluate whether an exoplanet can retain a thick atmosphere over geological timescales, they often assume that planets above a certain mass threshold will generate protective dipolar magnetic fields through convective dynamos. The assumption is reasonable based on our experience with Jupiter, Saturn, and Earth. Bigger planets have deeper conducting regions, stronger convection, and more powerful dynamos. The logic scales smoothly upward with mass. Uranus demolishes this assumption. Here is a planet of 14.5 Earth masses, solidly above any reasonable threshold for dynamo generation, producing a magnetic field that is weak, chaotic, multipolar, and offset from the planet's center by a third of its radius. The magnetosphere it generates is not a stable shield. It wobbles and tumbles as the planet rotates, creating gaps in magnetic protection that the solar wind can exploit. Solar wind particles that would be cleanly deflected by a Jupiter-style dipole can penetrate deep into the magnetosphere when the field geometry twists into unfavorable configurations during the planet's 17-hour rotation. If this magnetic configuration is typical of ice giants rather than unique to Uranus, then the atmospheric retention calculations for billions of exoplanets need fundamental revision. Worlds we currently classify as likely to retain thick atmospheres might be far more vulnerable to atmospheric erosion than our models predict. A sub-Neptune orbiting within the habitable zone of a magnetically active red dwarf star would face intense stellar wind bombardment. If its magnetic shield wobbles and tumbles like Uranus's, the cumulative atmospheric loss over billions of years could be devastating. A world that looked habitable on paper might be slowly stripped bare in reality. We would never know from mass and radius measurements alone. We would need to understand how ice giant dynamos actually work, and right now, we do not. The thermal evolution issue extends these concerns further. Planetary cooling models predict how quickly a world transitions from a hot, recently formed state to a cooler, more stable configuration over billions of years. These models inform our estimates of when an exoplanet's surface or atmosphere might become hospitable to chemistry and potentially to life. A planet that cools quickly becomes geologically dormant sooner, losing the volcanic activity and atmospheric recycling that may be necessary for long-term habitability. A planet that retains heat longer stays geologically active longer, potentially maintaining surface conditions favorable to biological chemistry for extended periods. If Uranus-like heat trapping is a common feature of ice giant interiors, the thermal evolution timelines we apply to exoplanets could be wrong by billions of years. A planet that our models say should have cooled and gone dormant 3 billion years ago might still harbour a hot, active interior locked behind a compositional barrier or a superionic ice layer. The surface implications would be profound. Volcanic outgassing, tectonic activity, magnetic field generation, and atmospheric renewal could persist far longer than current models predict. Conversely, if the trapped heat eventually escapes catastrophically through some delayed convective overturn, the planet could experience sudden, violent resurfacing events that would reset habitability calculations entirely. We do not know which scenario is more likely because we do not understand the long-term stability of interior stratification in ice giants. That understanding can only come from studying the one stratified ice giant we can actually reach. Every one of these uncertainties traces back to the same root cause. We do not understand ice giant interiors well enough to make confident predictions about how they behave. And we do not understand ice giant interiors because we have barely studied the 2 examples sitting in our own solar system. This is why the planetary science community has placed a dedicated Uranus mission at the top of its priority list. The 2023 to 2032 Planetary Science and Astrobiology Decadal Survey, the document that sets the scientific agenda and funding priorities for NASA's planetary exploration program, identified a Uranus orbiter and probe as the single highest priority flagship mission for the coming decade. This was not a narrow decision driven by a small group of Uranus specialists. It was a community-wide consensus reflecting the recognition that our ignorance of ice giant physics represents the single largest gap in our understanding of how planets work. The proposed mission would place a spacecraft in orbit around Uranus for a minimum of several years. Unlike Voyager 2's 6-hour flyby, an orbiter would map the planet's gravitational field, magnetic field, atmospheric structure, and thermal emissions globally and repeatedly. It would observe how these properties change with the planet's 17-hour rotation period, with seasonal progression, and with varying solar wind conditions. It would image the atmosphere at multiple wavelengths over extended periods, tracking weather systems and cloud features through their full life cycles rather than catching a single snapshot during one solstice. The gravitational measurements alone would transform the investigation. By tracking the spacecraft's orbital trajectory with millimeter-level precision using radio signals exchanged with Earth, scientists can detect tiny variations in the gravitational pull exerted by different regions of the planet. These variations encode information about how mass is distributed inside the planet at a level of detail that a single flyby cannot approach. A gravitational map with sufficient resolution would reveal whether sharp compositional boundaries exist at specific depths, whether the interior is smoothly stratified or contains abrupt transitions, and whether the mass distribution matches the predictions of impact models, superionic ice models, or something nobody has thought of yet. The magnetic field mapping would be equally decisive. Voyager 2 sampled the magnetic field along one trajectory through one part of the magnetosphere during one brief encounter. An orbiter would map the field from multiple orbital geometries over years, building a three-dimensional model of the dynamo's output. This model would reveal whether the field is genuinely dipolar but tilted and offset, or whether it contains significant higher-order multipolar components that Voyager could not detect. The distinction matters because it constrains the depth, thickness, and conductivity of the shell producing the dynamo. Different interior structure models predict different multipolar signatures. The magnetic field map would directly test which models survive. An atmospheric probe, released from the orbiter to descend into the upper cloud layers, would provide ground truth measurements that no remote observation can match. The probe would directly sample the composition of the atmosphere at multiple depths, measuring the ratios of hydrogen, helium, methane, water, ammonia, hydrogen sulfide, and noble gases with precisions far exceeding what spectroscopy from orbit or from Earth can achieve. The water abundance is the single most important measurement the probe would make. Water is the dominant oxygen carrier in the solar system, and the amount of water in Uranus's atmosphere constrains the total oxygen inventory of the planet. This inventory, in turn, constrains where and how Uranus formed. If the planet accreted most of its ices beyond the water ice line in the outer protoplanetary disk, its oxygen to hydrogen ratio should be significantly enriched relative to solar composition. If it formed closer to the Sun and migrated outward, the enrichment pattern would differ. The water measurement is a direct tracer of formation location, which is one of the most hotly debated questions in ice giant science. Noble gas abundances provide a complementary constraint. Noble gases like argon, krypton, and xenon do not participate in chemical reactions. Their abundances in a planet's atmosphere reflect the conditions under which the planet acquired its gaseous envelope, unadulterated by subsequent chemistry. Comparing noble gas ratios in Uranus to those in Jupiter, which were measured by the Galileo atmospheric probe in 1995, would reveal whether the two planets sampled similar or different regions of the protoplanetary disk. If the ratios differ in specific ways, it would support models where Uranus formed in a different location than its current orbit and migrated to its present position. Temperature and pressure profiles measured during the probe's descent would constrain the atmospheric thermal structure with a precision that remote observations cannot match. These profiles would reveal where cloud decks form, where hazes condense, and how the temperature gradient transitions from the upper atmosphere to the deeper levels where the internal heat deficit becomes apparent. The probe would measure, for the first time, whether the atmosphere at depth is as thermally stagnant as surface measurements suggest, or whether hidden circulation occurs below the haze layers that obscure our view from outside. Every one of these measurements addresses a specific open question in ice giant science. Together, they would transform our understanding of Uranus from a collection of anomalies and competing hypotheses into a coherent physical picture of how the planet actually works. And that picture would become the calibration standard for interpreting every sub-Neptune exoplanet discovered by current and future surveys. The timing is significant. The James Webb Space Telescope is currently characterizing exoplanet atmospheres at unprecedented detail, measuring molecular absorption features in the spectra of worlds orbiting distant stars. Future missions, including the proposed Habitable Worlds Observatory, aim to directly image Earth-sized planets around nearby stars and search for biosignature gases in their atmospheres. These ambitious programs will generate data about thousands of worlds, many of them in the ice giant size range. Without a calibrated understanding of how ice giant atmospheres, interiors, and magnetic fields actually work, the interpretation of that data will rest on models built from insufficient foundations. A Uranus mission does not just study one planet. It provides the physical framework for interpreting an entire category of worlds. Every dollar spent characterizing Uranus pays dividends across every exoplanet survey that follows, because the models used to analyze those surveys will be built on what the Uranus mission discovers. The investment is not in a single world. It is in our ability to understand the most common outcome of planet formation throughout the galaxy. There is a launch window consideration that adds urgency. The planet will be moving toward equinox through the 2030s and 40s. A mission arriving during this period would observe the planet under different seasonal illumination than Voyager 2 encountered during solstice, providing complementary data about how the atmosphere responds to changing solar input. Additionally, a gravity assist trajectory using Jupiter, which is the most efficient way to reach Uranus, requires specific planetary alignments that occur in the early to mid-2030s. Missing this window would delay arrival by over a decade, pushing the mission further from the optimal seasonal configuration and extending the already decades-long gap in ice giant exploration. The scientific case is built, the technological capability exists, the community consensus is established. The history of planetary exploration shows that every flagship mission, from Voyager to Cassini to Juno, has returned scientific value far exceeding its cost, often in ways that were not anticipated when the mission was designed. Voyager 2's Uranus flyby was originally considered a secondary objective, a bonus encounter on a mission designed primarily for Jupiter and Saturn. Yet that 6-hour visit generated the anomalies that have driven 4 decades of research and ultimately led to the recognition that ice giants represent the most important unexplored frontier in planetary science. A dedicated orbiter and probe mission would be to ice giant science what Cassini was to Saturn science, a transformative leap from fragmentary knowledge to comprehensive understanding. Cassini spent 13 years at Saturn, discovering ocean worlds on Enceladus, methane seas on Titan, and complex ring dynamics nobody predicted. Every year of the mission produced surprises that reshaped our understanding not just of Saturn but of planetary science as a whole. A Uranus orbiter operating for even a few years would almost certainly produce comparable revelations about ice giant physics, with implications that extend to the most common type of planet in the known universe. And this is where the story moves beyond measurements and missions into something more fundamental. Uranus forces us to confront a truth about science that is easy to forget when the textbooks look so complete and the models seem so robust. Our understanding of planets is built on a sample size of 8. 8 worlds orbiting one star in one corner of one galaxy. We have studied those 8 worlds with extraordinary ingenuity and dedication, sending spacecraft to every one, mapping their surfaces, sampling their atmospheres, measuring their fields and particles. The achievements of planetary exploration rank among the greatest accomplishments of human civilization. But 8 is a tiny number, and when one of those 8 defies every model we have built from the other 7, the correct response is not to treat it as an inconvenient exception. The correct response is to ask whether our models were ever as general as we believed them to be. Uranus did not break the rules of planetary physics. It revealed that the rules we wrote were based on an incomplete sample, biased by the accident of which planets happen to orbit our particular star. Jupiter and Saturn taught us how gas giants work. They were excellent teachers. Their lessons apply broadly across the galaxy. Exoplanetary gas giants behave in ways that our Jupiter and Saturn-derived models predict reasonably well. But ice giants are different. They are built from different materials, structured differently, and apparently capable of evolving along pathways that gas giant models never anticipated. We assumed the lessons from Jupiter and Saturn would scale downward to their smaller cousins. Uranus showed us that assumption was wrong. This is not a failure of science. It is science working exactly as it should. A prediction was made, an observation contradicted it. Now the models must be revised. The only failure would be to ignore the contradiction, to treat Uranus as a curiosity rather than a signal, to continue applying gas giant-derived models to ice giant-sized exoplanets, while knowing that our one accessible ice giant violates those models in every measurable way. The galaxy is full of Uranuses. Not exact copies, but worlds of similar size, similar composition, and potentially similar histories of impacts, migration, and exotic interior physics. Some of them may be tilted on their sides. Some may have magnetic fields that tumble chaotically through space. Some may hoard their primordial heat behind barriers of superionic ice, while presenting cold, featureless faces to their parent stars. Some may harbour oceans of compressed water-ammonia fluid at pressures that transform familiar molecules into alien states of matter. We will never visit most of these worlds. The distances are too vast, the travel times too long, the energy requirements too extreme. But we can visit the one ice giant in our own solar system that has already shown us, through 4 decades of accumulated anomalies, that this category of planet operates by rules we have not yet learned. Uranus is not just a planet. It is a Rosetta Stone for an entire class of worlds that dominates the galactic census. Every measurement we make there translates directly into improved understanding of planets we will never be able to study up close. Every anomaly we resolve at Uranus removes an uncertainty from every model we apply to distant sub-Neptunes. Every surprise the planet delivers, and it will deliver surprises because it always has, expands the boundaries of what we understand planetary physics to be capable of. There is something almost poetic about the situation. The planet that humanity has spent centuries laughing at, the world whose unfortunate name guaranteed it would never be taken as seriously as Jupiter or Saturn or even Mars, turns out to be the single most scientifically important planet we have not yet properly explored. The punchline of every classroom astronomy lesson holds the key to understanding the most common type of world in the observable universe. The cosmic joke, it turns out, was on us. 4.5 billion years ago, something happened to the 7th planet from the Sun. Maybe a world-sized object struck it at a grazing angle and restructured its interior in ways that locked away its primordial heat and confined its magnetic dynamo to a thin shell of exotic fluid. Maybe gravitational resonances during a period of orbital chaos gradually tilted it onto its side while its moons followed obediently along. Maybe layers of superionic ice crystallized at critical depths, creating barriers that no other planet in our solar system possesses. Maybe it was all of these things, layered on top of each other in a sequence of events that we can only reconstruct by going there and looking. Whatever happened, the result is a planet that broke every rule we built to describe how worlds are supposed to behave. A planet that tilts where it should stand upright, that whispers where it should roar, that hoards where it should radiate, that scrambles its magnetic field into a geometry that no textbook predicted. A planet that looked boring in Voyager's photographs but turns out to be the most perplexing and potentially the most revelatory object in the solar system. Uranus has been waiting for nearly 4 decades since the last spacecraft visited. It has been waiting, in a sense, for 4.5 billion years, carrying the scars of whatever cataclysm shaped it and the secrets of whatever exotic physics governs its interior. It is the closest example of the most common type of planet in the galaxy, sitting right there in our own solar system, reachable with technology we already possess, asking questions we already know how to frame. The planet that broke every rule is not an embarrassment to planetary science. It is the field's most important unsolved problem, and it is patient. It will still be there, tilted and silent and magnetically confused, whenever we finally decide to go back. The only question is how much longer we are willing to wait before we let it teach us what we have been getting wrong about planets for the last 50 years. Because somewhere out there, orbiting stars we have already catalogued, billions of worlds just like it are waiting to be understood. And the lesson starts here, at the strangest planet in our solar system, the one we have been laughing at, the one that has been quietly rewriting the rules of physics while we were not paying attention,